CIT 1123, Module 2, Submodule 2, Point-to-Point OSPF Networks. In this section, we're going to talk about setting up the network statements inside of OSPF. You can remember, hopefully you can remember back when we did this with RIP, and one of the things you would want to do when you're setting up a routing protocol is first you have to enable the routing protocol, and after the routing protocol is enabled, you're going to go ahead and put in the networks that are available from that particular router to other routers. There's a couple of different ways that you can do it. I don't want to get too deep into everything that they give you here, but one of the ways that you can set up a network statement is just by adding the command network and then using the network ID followed by what's called a wildcard mask, and then the area value, and then the number of the area. So like we've talked about areas a little bit, like area 0. So in the next slide or two, we're going to get an example. You'll see an example of exactly how to set this up. This talks about just how to set up the wildcard mask, which is just the inverse of the subnet mask. And there's a couple different ways you can do it. You'll spend more time on this really in the lab videos, in the packet tracer videos, than we will here. But you know what a subnet mask is. Everybody knows what a subnet mask is. And what you'd want to do is show the inverse of a subnet mask for, say, like a wildcard mask. And in this case, I'm just looking at these now really for the for the first time, and they're total garbage. They are totally wrong. So calculating a wildcard mask for /24 is not what they're showing here, because the subnet mask for /24, I'm going to use a pen here. I wonder if this will work. This would be 0. Let's go ahead and amend this right now. So the subnet, oh my gosh, this is so horrible. Okay, this is actually, okay, this is right now. Okay, so subnet mask is the bottom number here. So if it's a /24, it's going to be 255, 255, 255, 0. You could just take 255, 255, 255, 0, and then you could subtract the subnet mask from it. You would get the wildcard mask. With the /26, both of these numbers are wrong. So if we're in a /26, subnet mask for a /26 is going to be 255, 255, 255. I don't know if I can write it right in here because I got a little line there, but that's going to be 192. 192 would be the number. That's 192 right there. So 255 minus 192 is going to come out at 63. And that's one way that you can calculate the wildcard mask. For my money, forget it. Let's not do it that way. What I would say is this. You need to have a knowledge of how binary works, right? So if we took this subnet mask here and said that's a /24, right? So it's 255, 255, 255, 0. That's 3 blocks of 8 ones and 1 block of 8 zeros. And all we're going to do in the wildcard mask is just reverse it. So you can just think about it that way. So this one's not so bad. So we can say like 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6, 7, 8. 8 zeros. And then we're just going to flip them, right? So if we flip them, that's going to be 1, 2, 3, 4, 5, 6, 7, 8 zeros. 2, 3, 4, 5, 6, 7, 8 zeros. I'm going to run out of space. 2, 3, 4, 5, 6, 7, 8 zeros. Hopefully that's 8. And then 8 zeros is going to be 1, 1, 1, 1, 1, 1, 1, 1. And you're going to end up with this value here. Same thing is true here. Let's just not do the first 3 octets. Obviously, the wildcard mask for 255 is going to switch out to a 0. So that's going to come out looking like, what was 255, 255, 255, 192. If we look at the number 192, we look at it in binary, that value will come out looking like this. 1, 1, 128 plus 64, 0, 0, 0, 0, 0, 0. So think of it that way, is that's 2 1s and 6 zeros, and the wildcard mask, just flip it. So that's 0, 0, 1, 1, 1, 1, 1, 1. If we add those numbers together, we're going to get 63. Like I said, more on this when we do the exercises and you add it up. But the point is this, is that what you should be doing for your network statements is creating networks with the exact correct subnet mask for the networks that you want to support. Now, to make it even worse, they give you another way to do it in the slide after this one, and we'll talk about that in a second as well. But the way that I'd like to see you do it for this class, just for getting started, is converting your wildcard mask. Be able to convert a subnet mask into a wildcard mask. It's really easy. It's just the inverse, and I'll talk about some other fast ways that I've got for you to fix those in the future. So in this example, this particular router has 3 directly connected networks, and it is going to be in router OSPF, and you see the number 10 here. That number 10 is what's known as the process ID, and this is just a value that you're going to use on this particular router. So here's the thing. If a 4th network was added to this router, you would have to come back in and type in router OSPF 10 again. So you need to keep all of the routes together with the same process ID. This process ID value is locally significant, which just means that you don't have to use 10 on your neighbors, your neighbor routers. Your neighbors are going to become your neighbors because your area value matches. You said area 0 here. Your neighbor's going to advertise networks in area 0. They're both going to be in area 0. You use process ID 10. Your neighbor uses process ID 7. Who cares? It doesn't matter what process ID you use, but you have to keep using the same process ID straight through on that router to keep everything in what's called the same database. Okay, if you use a different process ID, you come back here, hey, I'd like to edit this, and I'm going to use process ID 8. Great, you just created a new database, and whatever you type in there isn't going to match or mirror or commingle with what you've done previously. So that's a dangerous thing. So keep that in mind. And here they're getting into the same thing here. We just talked about the area 0. Let's go back for a second. So look at these wildcard masks here. So this one's the /24. Take a look at this one, 0003. Think about it in your head. What is that one going to come out to? That's going to be a /30 network. It's a /30. Think about it. That's 6 ones in a row with 2 zeros. And then we flip it. That's 6 zeros and 2 ones. And those ones will be in position for 1 and 2, right? 1 plus 2 is 3. Easy enough. That's a /30. Easy to identify. Same thing with the other one. So this router is connected to 2 other routers because it has 2 /30s, and it has 1 LAN, which is the /24. Hopefully that makes sense. Like I said, I think there's like 5 or 6 packet tracer labs. You'll get the hang of this. Don't worry. Now, in this slide, they change it around a little bit, and they say, well, as an alternative, if you don't know what you're doing as far as wildcard masks, you can use the just use the wildcard mask of all zeros, and it will enable OSPF on the interface. Oh, goody. So, and that's fine that it does that, but it's not going to advertise the rest of the networks for 10.10.1.0/24. So it isn't going to advertise out at a /24. It's going to advertise out at just this interface. Now, here's the thing. If you do this, and you have you want other devices to be able to access that 10.10.1.0/24, you're going to have to make another network statement that's 10.10.1.0 0.00255. You're still going to have to put that one in there anyway. Or 10.0.0.0/8. You could do that, and it will pick up the correct networks that are on the interfaces. I would recommend just for now, doing it this way. Find your networks, put in the correct wildcard masks, put them in the correct area, advertise them that way. Can you do just the interfaces? You can. The advantage to that on the point-to-points, generally those are networks you're not going to advertise anyway, so it's not a big deal. But for the LANs, it's going to be a problem if you do it this way and you don't add one more network statement. A lot of people will say, well, for security reasons, I like to do it this way, and then I'll do an overall network statement and anything that falls into that. And that you can do it. It's kind of a newer process. For now, though, for the way that we're doing it now, just do it like slide 14 does it, and put the wildcard masks in correctly. Learn how to do a wildcard mask. You're going to need them in chapters 3, 4, and 5 anyway. So when we do access control lists, it's not like you're going to get out of learning wildcard masks, because we're learning wildcard masks here, and then we're going to learn wildcard masks again in the next chapter. So it's not like you're going to get out of learning them. You're going to have to learn them. This is a nice slide that just shows the config for this particular device, and you can see here that they've taken router OSPF 10, and they've taken those networks out, and then they've gone to the interfaces, and they've shown you a brand new way that you can set this up. You could say, well, I'd like to set this up with the interface values under OSPF. You can do that too. It's a little bit of a non-standard way. It's a little newer. This is not a method that I learned when I learned this a long time ago. So it is something you can do by putting the interfaces under putting OSPF in under the interfaces, but it is I guess it would be considered just kind of a newer way to get it done. So keep that in mind also. So this is another way that you can set these up. As far as the labs go, they never ask you to do it this way, so don't worry too much. Other things about OSPF, OSPF enabled interfaces are set to use bandwidth efficiently. So we're going to set some rules that will identify when OSPF is using too much of the network, or in this case, when they talk about passive interfaces, a passive interface is an interface on a router that you want to advertise that network to your neighbors, but you don't want to send any advertisements out that interface. This would be true of any LAN interface that you have. So I've got a /24 because I got a whole bunch of users out there. You don't want to send any OSPF updates out into the LAN. There's no routers over on that side that are going to be interested in getting that information. It would just be wasting bandwidth. And that's what they're getting into here with this passive interface command. So an example here, it shows you router 1 config, router OSPF 1, passive interface, loopback 0. And this is not a great example of this, but okay, a loopback interface, it's an interface that we just created so that we have this value, and we are not going to send any updates out it. It's a fake interface. So as far as it's saving bandwidth, it doesn't do that at all, but whatever. It's a slide, and it shows you the way that you're going to add the passive interface into the configuration. We'll do it once again. It's in the labs, and it's set up pretty easily. It's pretty good. Point-to-point networks. As far as point-to-point networks go, one of the things you can do with a point-to-point network is it will turn off the BDR election process when you don't need it. So if you don't want to, it's a point-to-point network, you can set it up that way, and you can use the point-to-point command on the interface. So if we take a look at it here, here's how you can set that up. Interface G0/0/0, IP OSPF network point-to-point. That'll set it as point-to-point, and it will essentially turn off the BDR election process. You don't have to do that on serial interfaces, but you can if you want to. If you are in a situation where it is not it is a point-to-point situation, then you can set it up that way. So that's something you can do also. The last thing I want to say about that is as follows. When you set up loopback interfaces because you want to set the router ID, or you have just need extra networks, loopback interfaces, you're going to want to set all those up with point-to-point, because if you don't, they will default advertise to just the IP address of the loopback interface. It will not advertise the entire network, and that's just a kind of a little gotcha within OSPF. Okay. Multi-axis OSPF? Why not? Let's go ahead and finish this piece now. So when we talk about multi-axis OSPF, it's just OSPF routers. In this case, we have 4 routers here. They're all connected to the same switch. They're on a like subnet. They have one subnet, and we have to figure out which ones are going to communicate with each other directly. And that's where that DR BDR comes in. And we talked about that before. So if we have an Ethernet network, we have multiple routers facing that Ethernet network. So router 1, router 2, router 3, router 4, they all have an IP address in the same subnet that this is being supported by. So they're all 10.0.0.1, .002, 003, 004. That's like a /29 or something like that. And they're all going to talk to each other. And what we want to do is pare down the number of advertisements, the duplicate advertisements that would happen in that situation. So when we get into that point, the routers will figure out how to set themselves up as a designated router or a backup designated router. Now, the role of designated router is elected based on the router ID of the device. And the router with the highest router ID will become the designated router. So if we look at this just by default, and we're looking at these different devices, there's router ID 1, router ID 2, router ID 3. In this case, since the router ID is 3.3.3.3, this device, router 3, would become the designated router by default. Router 2, which is IP address 2.2.2.2, is its router ID, would be the backup designated router, and router 1 with an address of 1.1.1.1 is not the highest or the second highest, so it becomes what's called a DR other or a druther router. It's just a router that takes its orders from the DR or the BDR, mainly from the DR, okay? Now, in this case, they set these router IDs up by being loopback addresses, okay? So let me give you an example. In this case, all of the LANs are 172.16.1 dot something, right? So yes, 172.16, but the network in between here for all these routers is 192.168.1.0/24. So by default, the router will take the highest IP address on any interface and advertise it as its router ID. So in this case, even though they'd already hard-coded these, and we'll get to that in just a second, router 3 with the active interfaces would be 192.168.1.0. 1.3 would be the highest possible address, so this would become the designated router in that case. Now, they did something to alleviate that. Here's the problem with making a live interface the value of your router ID. If this interface happens to go into a down state, your router ID then changes, so the router ID would not be 192.168.1.3 for router 3, but it would switch over to 172.16.3.1. It would start using this value, and if it actually had the ability to get to these other routers through another channel, it would start sending updates with its router ID as being this. And now router 2 and router 1 have absolutely no idea who this is. And they're like, ooh, a new neighbor. Let's set up a neighbor relationship with them and let's figure out what they know. This is something that we don't want to have happen. So when we have a live interface, that's a bad thing. So we don't want to use live interfaces as router IDs. What we'd rather do, and the first thing they used to teach us was this, is we'll make a loopback address. So we'll make a loopback interface. So we'll do INTLO1. This is in the packet tracer labs also. INTLO1 and put an IP address on it, and this IP ad, and then in this case 3.3.3.3, and you can set that up, and then by default, any loopback address is given credence for router ID over a physical interface. So if you set up a loopback, the loopback becomes your router ID value. And then the last thing you can do is you just hard code a router ID into the machine by using the router ID command, and we'll see that in the next 2 slides also. So hopefully this isn't getting too far off, and I just got really close to the camera. I just realized that was probably a bad idea. But this is an important piece, and like I said, we'll do it in the labs. It should come out in the wash as to how to set up router IDs and what those router IDs are. And full route, we talked about this. Talked about how it's a limited amount of communication, so we don't send up too many address links. Here's a show IP OSPF neighbors. It shows your neighbor's router ID here. So this is obviously 2.2.2.2 that we're looking at. And it has a neighbor of 1.1.1.1, 3.3.3.3. 3.3.3.3 is in full state, and it is the designated router. Fantastic. Gives us an IP address, what interfaces we use to connect to that other device. Notice the interfaces are the same because we're on the same subnets, right? So no big deal there. I think we got that. I want to just get to the slide here, where I guess there isn't one. Man, I thought there was. I thought there was a slide where it had you typing in the router ID directly, but I guess that's not happening here. So just keep that in mind. But you can hard code the router ID. Like I said, it is on a slide that is in the PowerPoint presentations. All right, that's it for part 2. We'll do part 3. Oh, sorry, that's it for parts 2 and 3. We'll do part 4 in the next video.